Welcome to this afternoon session. I'm Hans-Kristian. I work on this tool called SPIR Cross. How many have used it? Hey, thank you.
Good job.
Woo. So this is going to be a bit of a different talk. It's called the war stories for a good reason, because there are many war stories with this tool. Some things are informational, some things will be just pure rant because I want to rant about this. Yeah. It's not about reflection, this is about cross-compilation, which is actually a difficult problem to solve. Talk about the end goals of this stuff, then some campfire stories about how all the shading languages are basically broken, need to be fixed. Various difficult problems I've found implementing this thing. Translating SPIR can be interesting in various places. I also try to reflect a bit on how SPIR is designed and how that has shaped cross-compilation for SPIR. And maybe if you're not a compiler nerd, you might learn some new interesting things, because I've had to learn basically everything from scratch. So the backstory for this tool, this started out before Vulkan was shipped. SPIR 1.0 was a thing around this time frame, end of 2015. We had this target for GDC 2016. We want a Vulkan glass comparison demo, big showcase at the expo floor. But we didn't have a good way to target both Vulkan and HLSL shaders. Our cross-compiling solution at the time was barely working, and we couldn't reasonably make that work with Vulkan as well, because all the new resource types. So we just figured, okay, we have SPIR, GLSlang is working more or less. Let's try to do a cross-compiler based on SPIR. So this actually worked. It got up and running really fast, because it turns out the code that GLSlang generates is super simple. It's a one-to-one map with GLSL, more or less, which makes it very easy. And I could implement this thing by just reading the spec. The SPIR spec is really good to read. It's just, you just read through and you know SPIR. It's a very simple thing to learn, except for a very few really weird edge cases. So we released this for GDC 2060 under the not so pretty name SPIR to Cross, but we donated it to Kronos under a more friendly name, SPIR Cross, and it's under Kronos Group, so it's an official Kronos project now. And I have maintained it ever since. So to start off, I started with GLSL, so let's go into GLSL. So yeah, clean shading language output is something that cross-compilers are really bad at, or have been really bad at. For example, HLSL CC is the perfect example for this. And I think readability is important, especially since SPIR is so clean that you can get good output. You can get almost a one-to-one match, GLSL to SPIR to GLSL. And I think that's pretty important, because most of the older cross-compilers went through FXC DX bytecode, which looks really weird, and then try to translate it to high-level code, and it's basically line noise. So I want to make use of this, but SPIR assembly is pretty weird. It's really difficult to read. Any IR format makes no sense to anyone. Only compiler people will understand it or even care about SPIR assembly. And a very important use case was our driver developers in ARM, and I guess other companies as well, I suppose, was using it to take SPIR and figure out what does this code actually do, because understanding SPIR from assembly can be really tedious, especially for larger shaders. So the readable code really matters. Here's a screenshot from RenderDoc. So there's this really cool feature where you can debug a SPIR shader, and you can edit it, and you get out this clean Vulkan GLSL code in the debugger. You can edit it there and then recompile. And at that point, readability really matters, because if what you get out is basically garbage, you're not going to be able to debug fast with this thing. But assuming you haven't stripped all your shaders of any debug information, then you can actually get code looking like this in the debugger, and you can edit it, and it works. So code gen seems simple if it looks like that, but it turns out there are some major issues. So the first issue I had to tackle was loops. And loops, as we all know, are really critical for performance. I don't know how many rants there have been about loop unrolling and doing that offline. And it turns out loops are critical for performance. If you have a loop, it's probably the critical path. Yeah. And emitting weird loops is a great way to crash drivers. And an intermediate representation doesn't really have a concept of a for loop, a while loop, a do while, these things. So I actually need to translate IR code into something that looks sensible in GLSL. Because a loop in SPIR looks basic like this. You initialize a variable. You have a block saying this is I will have a loop and it will merge at some point. It will merge here and the continue block is there. You have this first block saying I will compare if I will branch either to the body or branch to the merge block if it fails, which is basically means exit the loop. The body will do stuff and it will branch to the continue block, which will increment I and loop back again. So that's the typical anatomy of a loop, but there is no concept of a for loop here, no while loop, nothing like that. If you just translate this as is, you will get that loop. This is the spider for loop. That's a great way to crash drivers, and I've crashed many drivers with that. You have this outer for loop, and then you have this inner thing which checks the condition, goes to the body and continue block, and the else there breaks, and basically no driver can unroll this loop. It doesn't make any driver or compiler engineer will look at this and say, why are you doing this? This makes no sense. And it turns out you will crash many drivers with this. So I had to find a solution. So now I had to learn about control flow graph analysis, which is basic compiler stuff, but it can be a bit difficult. So I have to sort of figure out, okay, where are the continue blocks? It accesses some variable. Okay, that's probably a loop variable. That's probably the I++ thing. And then figure out what is the dominating block that touches that variable, which means what's the innermost scope that touches it. Now it's deep into compiler territory. Turns out this is really nice because SPIR is structured. So thanks to the SPIR folks for that. If it was unstructured, this tool would not exist. And then check if there are some direct branches from that block to the loop. That means I can statically deduce the initializer. Okay, that's cool. And then is it accessed outside the loop? If it's not, okay, I've reduced the scope now to the for loop, and I can go from there. And this took 4 months to figure out. Yeah, it took a while. So now that ugly for loop will actually look like that, and it unrolls very nicely. And now it works fine, and so I can be a compiler nerd too. Woo. Yeah, fun times. But it turns out you have to do this. There is this shading language that I now call extremely stupid shading language 1.0, which for anyone who has targeted Glass 2 knows that the shading language can be painful. So this is kind of like HLSL legalization except for loops, which is annoying. And it also needs to translate I equals I+1 into I increment 1 for some reason. I mean, the spec says if you're going to have a for loop, you have to do it exactly this way. Oh well, but it works. It works on WebGL 1.0. So yeah, happy with that. Next thing was fine nodes. This is the inverse of goto. And if that doesn't scare you, I don't know what will. So there is this thing called single static assignment. Compiler nerds just love this thing because they can do crazy things, but it's just weird. Because a fine node, basically, you assign a variable based on where you came from in the CFG, which makes no sense. I'm sure there are good theoretical things you can deduce from this, but it's pretty painful. So the way I deal with this, if I have a fine node, which is a temporary, I make it into a variable, and then track all the cases where blocks can branch into my current block, and sort of track all of this. Whenever there's a branch, even in the most crazy situations, like breaking out of a loop or going into a loop in the continue block, just any possible case where you can branch, you need to track, do I need to write to this phi variable? Yeah, so it's not too hard, but let's say that SPIR-opt is really good at making my life difficult. Because it really likes to translate everything into fine nodes. Variable scoping, very fun. I really care about good variable scoping because it makes everything readable. You don't want 1,000 variables emitted at the start of a function and then having them used scattered around the code. It's just impossible to reason about. So you would think that having domination analysis, a CFG in place, that you would solve this problem, but it's checking, okay, where's the dominating block? I'll put it there, it works. But it actually doesn't. So you will, if you've used SPIR opt and then SPIR cross, you will see this pattern a lot where you have a weird do while block. You do something and you break out of it. This comes from inlining. But the weird thing, if you do this analysis, the dominating block is inside the loop. That's the dominating axis. Because there is no, you don't really branch above that thing. You branch directly into the loop and out of the loop. So for purposes of cross-compilation, the inner scope is the dominating block, which makes perfect sense in IR, but not in code. So the hack here is, OK, for every loop there is, I'll just pretend there is a branch from the top of the loop to the bottom of the loop, and voila, the dominator. Now I can emit it there, and it works fine. I've probably had 100 bugs with this so far in various cases where SPIR opt does interesting stuff. Another really weird case that will happen is that the continue block can become a dominator. So you can't really emit anything here. I mean, you can't emit anything there. You can't do anything there. You can only have statements. So, of course, I have to check all these cases and move that above the loop and all sorts of things. That took a while to figure out as well. There is a lot of weird analysis in SPIR cross. And of course, this isn't just restricted to variables, because SPIR has this thing, it has temporaries and has variables. So in the beginning, GL-slang only did variables. It didn't really use temporaries in an interesting way, other than loading and then storing. But of course, now with our newer tool chains, it will do weird things where a temporary needs to be analyzed. So I actually need to now analyze everything, every single variable there is, even temporaries, and figure out their inner scope and outer scope and these things. Now, the good thing about SPIR is it has a very simple way of encoding instructions. So I don't have to check every single opcode in the universe to do this analysis, because there are hundreds of them. I usually can check the two first words, which means result type and result ID. So some minor things in design just made things so much nicer to work out. So instead of spending 2 days doing this, I spent a few hours, or actually a few days, but it could have been a week. In total, with all the bugs, it's probably a few days. So, OK, so it started out, the previous issues are reasonably simple. You can work them out, but now it gets really hairy. So combined image samplers. We're all used to separate textures and samplers now. DX have had this for forever, almost. GL hasn't have that. It's now in Vulkan. You have separate images and samplers, and you combine them in the shader to sample a texture, which is good. But I have to make this work on all the targets. So what if I have a shader looking like this? That's what you would write in Vulkan HLSL, but you need to write code like this to make it work on GL. So how does that work? So it's not a trivial solution. What I have to do is, OK, figure out every possible use of this combined image sampler in the shader. That means going through function calls, tracking everything, tracking the arguments. That can be combined with the global sampler. It can be combined with something else. I figure out all use cases, and then emit new sampler 2Ds, and then just remap that dynamically. And of course, in reflection, I need to also say, hey, I combined these images and these samplers into those combined samplers, so you need to deal with that as well. So it's pretty painful, but it's doable. So yeah, it gets worse. Buffer flattening. So this is, mobile people will probably know about this. So in modern APIs, there is no non-opaque uniforms. So you can't have a uniform int anymore. You can't have a uniform struct. You can't have anything like that. It's only push constants and uniform buffers. That's what you get these days. Flat buffer, or not flat buffers. But some people, unfortunately, still have to target these ancient APIs. So what do we do? The obvious solution, or maybe not so obvious, is to just take a UBO and make it into a uniform struct. You'd think that would work, and it does work, I suppose. The problem is you have a lot of GL uniform calls if you're going to make this route. If you have lots of members in your struct, you will need tens of maybe 20 API calls just to update that UBO. So it's not practical, but it works. And even if we use GLES 3 and can use UBO, we all know that all mobile drivers are super awesome and the best in the world. Not sarcastic at all. And people want to use GL Uniform, the array version, just have a single update. So Arntzen from Roblox contributed this support, which is pretty cool. And this came in handy later. So what happens now is if you have to explicitly flatten the blocks, but you can do things like take this UBO, turn it into an array of vec4, so it's completely flat, and SPIR cross will handle all that access chaining for you. Lots of weird tests there, especially if you have row major matrices and you index into them. That gets really weird. But it works. It should work. There are tests. So there's also shadow samplers. It's not as bad. So it's close to GLSL, but it's not closer than that. That's a PCF joke, but yeah. So what you will typically see in SPIR-V would be something like, okay, I have a sampler and I have a texture, and I'll make that into a comparison sampler, and I'll just sample that. So in SPIR-V land, this is how it works. That's how it would look like. But no, GLSL does not support that. It has a separate type called sampler shadow, or sampler comparison state in HLSL, which makes this pretty annoying because there is no concept of a shadow sampler in SPIR-V, which is really weird. Not sure why. Or it's just GLSL being weird. It's probably GLSL being weird. So again, yeah. Now the problem is I have to analyze everything, all the uses of combined samplers, and just figure out, okay, was this used as a comparison sampler, and propagate this information up. And now the typing system needs to know which variable it's being used for. So it's not really a type system anymore, which is annoying. But yeah, when I emit the type sampler, I need to check, okay, is this ID used as a comparison sampler or not, and then emit the right type. So that's a similar thing for HLSL. Turns out metal is being weird, and it has texture 2D versus depth 2D, which just, the sampler is not comparison for some reason. Anyways, enough about GLSL. So metal support was added eventually. So Molten VK through, well, it was closed at that point, but Brenville Workshop through Bill Hollings created this massive pull request for MSL backend support. So at that time, we only had GLSL. So this was the first attempt to make things a bit more, let's say, portable, in the sense that you could have multiple backends to this thing. And this structure has lived that pretty well. So this was the groundwork, and it was merged around 2 years ago. So a lot of development has gone into it since. But metal sharing language is really weird, at least from a cross-compilation point of view. Because the biggest problem, or one of the biggest problems, is in SPIR-V, everything is global. Any texture resource, anything is global. But in metal, everything is in main. Everything is an argument to main. No globals, nothing, which means there is a lot of work gone into just analyzing all the resource use and then just propagate this down to the leaf functions and making that work properly. Which, yeah, there are lots of weird cases where built-ins and SPIR-V don't exist in metal, so you have to create dummy helper functions and all these things. So I consider it the hardest language to target for a cross-compiler. It's just so different from anything else, even though it's just C++ basically. So this might sound weird, but I have no way to actually test metal myself, even though I maintain most of the backend. But Travis CI is really great for this stuff because it can actually compile metal shaders. So that's really good, so I can actually check if it compiles. Not saying it works, I'm just saying it compiles, so I can ship it. But yeah, it's very painful that there is no open source compiler, because then I could just use that directly locally and check that things compile, but I have to run this on Travis to even check if it compiles. One of my favorite things, arrays are not value types. Yeah, so you will probably see code like this, where if you want to copy an array in SPIR-V, you will end up with this weird function being emitted in your code. Fortunately, there are templates. Otherwise, yeah, I don't know. This is one of those weird things. GLSL and HLSL arrays are value types, and you would think they are value types, but they're actually not. They fall down to pointers just like C++. Yeah, fun times. And yeah, at this point, the moments like these start to trigger PTSD. Well, I think MoltenVK will have a harder time with this. For some reason, you can't have a comparison sampler on older iOS targets without having it be const_expr inlined in the shader. So how that's going to work is interesting, because if you change the sampler in Vulkan, you would have to recompile shaders. Yeah, the glass is leaking in here very clearly. But this is really painful. So now I have actual support to say, okay, this sampler we have, okay, I'll give you the const_expr thing, and I will deal with that when I decompile the shader. And it's terrible. Enough about. I mean, there is. I mean, I could rant about this for hours, but that would be extremely boring. So moving on to something interesting again. HLSL was added. So that was contributed by Robert Conrad. He works on Haxi, Code, Core. I don't know what the exact project is. It's all of those things, basically. So now we have coverage for everything, all the major shading languages, which was really cool, because the future was looking bright now. But still early days, that was very bare bones support, and I had to take over main development of this thing. So I had to learn the dark art of HLSL, and it turns out without the spec and not without 10 years of experience doing weird stuff in HLSL, I found a lot of interesting things that I didn't expect. So matrices, always fun. I wish I hadn't had to deal with this. So matrices and HLSL are really strange, like really strange, because in a buffer, by default, you will get a column major layout. That's the default. If you have FXC and you type row major there, you will get something different. The default is column major. So you would think that the matrices are laid out column major in the shading language, but no, they're actually row major for some reason. So something interesting happens in GL slang, because SPIR-V is column major oriented. So if you index into a matrix, you will get the columns, but in HLSL, you will get the rows. So GLSL does this really funky thing where it will flip the row major of every single matrix in your shader into row major, or back, and it will flip the multiplication order to pretend you're doing column major in the indices, even though you're actually supposed to do row major, which gets really funky, because if you have HLSL like this, you go to SPIR-V and GLSL, you will see code like this, row major and what? Yeah, it gets weird. Really, really weird. I don't understand why HLSL does it like this. But based on this trick, if I want to go back to HLSL, I do the same trick again. So I just check, oh, it's a column major, I emit row major, and then flip the order again. So if I go HLSL to GLSL to HLSL, it's in the correct order again. It's weird, yeah. So matrices are weird, but storage buffers are probably even worse, because HLSL has so many buffer types, but it can't express an SSBO. Yeah, I don't know. So there are three types. You have structure buffers, which is probably the most used one. You have byte address buffer, which is now my favorite HLSL buffer type. And then you have those weird append consume buffers that hopefully no one should ever use. Counter buffers they are another nightmare to deal with in SPIR-V. But SSBO can express things that are uncommon. Things like you can have normal sized stuff, and it's ended by this unsized array, which is what you can do in C99. Turns out HLSL cannot express this at all. It's impossible for some reason. Structure buffer only gives you that. Byte address is basically just, yeah, byte address buffer. And append consume is just a fancy structure buffer. So byte address buffer it is, because that's the only way I can express this. And I have to flatten everything, so I reused the GLSL or ESSL flattening code. It will translate everything into load, store, weird things, and bitcast everything into correct types, and it's just ugly. So this is what you get if you try to load a row major matrix from SSBO. It's actually a column major. It becomes column major, but because matrix construction in HLSL is row major, it becomes this really fun looking code. I'm sure that will compile beautifully. Please don't do this. So yeah, then SPIR came, or it was always there, but it was didn't do much interesting. But yeah, this has made my life pretty difficult. Fortunately, it's a conspiracy to break SPIR across. I don't know how many bugs, probably 100 bugs, just because of interesting corner case I never thought about. So in the early days, there was SPIR didn't do anything. It could probably strip away debug information, but yeah, not really much beyond that. It did not promote loads and stores into registers and those fancy things, but it does now. It has since 6 months or 1 year ago. It's doing interesting things now. The optimizations make sense from an IR point of view, and that's stuff you obviously want to do. You probably want to inline stuff. You probably want to avoid loads and stores, these kinds of good things. It can promote stores through indexed arrays, and it's cool stuff, but it makes life hard, very difficult. So the lessons I've learned from this is that good-looking code in IR can be really, really bad in high-level code, because it does really strange things. So just some problems I've run into. It turns out continue blocks can do all the things in the world. They aren't just for incrementing I, which you would think it would do, but it can do everything. So SPIR had this brilliant idea of simplifying for loops. So instead of having the continue block just do the increment, it will actually do everything in the continue block. So if there is no control flow, this makes probably sense now. You can save probably 4 bytes by not having a separate block, but okay. So code was looking like this for a while. You might have seen some rants on Twitter. So you have loops looking like this. I'm surprised this code even worked, to be honest. But you would have all of this in a single line, and this is like big inline blocks, and yeah, I'm adding profanity at the end there because yeah, there was a lot of profanity to try to fix this. So I just gave up, saying, okay, if there is this case where you branch into continue block, I will just take that continue block and put it inside the loop. So it looks a bit funky, and it will break ESSL 1.0, so I don't do it for ESSL 1.0 actually. So WebGL might have code looking like this, but then again, who cares? Yeah, that was a shady workaround, but yeah, there are lots of shady workarounds to deal with SPIR. Yeah, phi can also be interesting. So I'm surprised there haven't been that many miscompiled shaders, as in I've generated legal GLSL, but it doesn't do the right thing. There have been very few cases of that, fortunately. Most of the bugs have been, oh, it doesn't compile because you haven't put the variable in the right scope or something silly like that, or you emitted the wrong code, it doesn't compile. So fortunately, I catch most of those issues early. But this one was deep inside an SMAA shader. Yeah. So it turns out OP5 nodes can take other OP5 variables as input. There's like two levels of come from, which is 2 levels of inverted goto, which gets painful, of course. The ordering is important because I'm writing to a variable when I resolve 5 variables, which means I can accidentally invalidate other things going into the next node. And so I have to track this as well. Then it worked, fortunately. Just one bug fix to fix this shader. But yeah, it's these kinds of bugs that sort of, yeah, it's not very fun to see on a Friday. Or I think this was on a Friday. I hope it's a Friday. Inlining is very painful. I mean, you would think it makes everything nicer, but it actually just makes things incredibly difficult to deal with. Because C-like languages have this escape hatch to structure control flow. Structure control flow is when you have sort of a for loop and you exit properly, you have an if statement, and you merge all the threads in a single place, so it's easy to analyze. But return is this magic thing that just exits out of any scope there is. So multiple for loops, it can exit through those. So the common workaround that you will see GLSlang do, or SPIR-opt, I should say, is to wrap this in a do-while loop that never loops, but it can break out. So that's an escape hatch to break out of any scope. Of course, you can't do that if you have multiple for loops and then you can't fortunately, you can't break out of multiple loops. That would be a nightmare. And if SPIR supported that, SPIR cross would die instantly, and we would, I wouldn't talk about this anymore. Yeah, so fortunately, I raised this concern that, hey, you don't break out of multiple loops. Please don't do that. So yeah, you can't in SPIR, fortunately. But then again, SPIR-opt has had many bugs where it would actually do this. So there have been many back and forth. Oh, this SPIR cross is broken. Oh, SPIR tools is broken. SPIR cross is broken. These things happen. But it has stabilized now, roughly. I haven't seen many issues with this lately. But 1 year ago, this was a big deal. So the inlining pass exposed so many bugs. But you have to be really careful with inlining. If you're gonna use SPIR cross, just be very careful because the code you get might not make any sense in high-level code. So this is without any optimization. If you have this weird-looking function, I mean, okay, you have a branch and you return. That means you're gonna exit out. Blah blah blah. This kind of code is surprisingly common to see in shader code. I don't know why, but you see it all the time. This is the output you would get from SPIR cross if you don't optimize. I mean, okay, you get these squiggly braces, but I mean, come on, that's fine. But the code is basically intact. The only thing that's weird is this thing. That's because of it passes things by pointer, and it needs to preserve the value things. We need to copy, etc., etc. Any optimizer can do this trivially, but you will get this ugly weird thing. Now, what happens if you turn on inlining is this. Yeah, well, so what happens, it does the thing, and here it shuffles in. This is an op-fi taking an undefined variable. It doesn't make any sense, but you can do it. It's probably optimal, I don't know. And then it has these ladder variables to check if it should continue. Apparently, for some reason, it did not do the do-while trick. I suspect it is to actually deal with multiple nested do-while loops, but yeah, I really doubt this code would run better than that other function. So be very careful if you're going to overuse SPIR-opt. Just a warning. But it might be very good for obfuscating. This is excellent for obfuscating because no one can figure this out. So yeah, buffer packing. Buffer packing is terrible. This is why I hate every shading language right now. SPIR does the right thing. It has explicit offsets. It has explicit everything. They're all lacking in some way. I can't reinterpret cost stuff and just do it manually. Maybe I can do that in Metal. I'm not sure. But the code will look horrible anyways. So some standard, just the simple case. Vec3 is the root of all evil in shading languages. GLSL is so nice that it even has 2 standards for how to pack things. So GLSL here makes sense, and HLSL makes sense, but in Metal, a Vec3 is actually a Vec4, because why not? I don't know. So there you will get a different size, and in the Metal backend we have this packed Vec3 and dealing with that, and yeah, that's another story. But it doesn't end there. If you have if you flip them around, it gets even weirder. So in GLSL, it sort of makes sense. Vec3s have 16-byte alignment. You get that on the next Vec4. HLSL is weird because you can pack things in Vec4, but if it straddles it, it will spill out into the next Vec4. So HLSL is different there. In Metal, yeah, it's Metal. Arrays, yeah, fun times. Array strides are different based on GLSL standards, and yeah, nightmare time. I'm not sure what Metal does there. I don't really want to know either until someone files a bug. Yeah, the mitigation strategies I have to deal with this are varied. Sometimes I can do layout offset. Sometimes I can do pack offset in HLSL. Sometimes we rewrite buffer members to try to work around it. I can't control array stride, so yeah, that's impossible. But the biggest annoying thing in GLSL is that the layout only applies to the top level block. I can't do it on substructs. And of course, you can have structs within structs within structs. And you can't apply any magic layout to them, which feels really weird. And in HLSL, if you use constant buffer of t, you can't even do pack offset because that comes from a struct, and you can't have pack offset on a struct. It's basically impossible to deal with any possible case. So if you're going to use this, please try to be friendly with the cross-compiler so that you don't intentionally try, oh, I want to have vec3 array, and I want to be packed by 12-byte strides or something crazy like that. Please don't do that. I will instantly close your ticket. So yeah, the conclusion, just wrapping up. SPIR-V design is, there have been so many things that could have gone so wrong that would have made SPIR-V cross basically impossible to do. But it's close enough to higher level constructs that you can do it without too much effort, or, well, 2 years of effort, but anyways. It is structured. That makes things so much nicer. If I had to deal with the go-to soup, I would not do this. You have structs and matrices as high-level types, and some people will dislike them because they're not useful, but I think they're really great because it helps reflection, and the code you get back makes sense. It's not garbage with vec4s. That's the only type you have in the shader. You have support for load store model, which is great. It's future-proof. So OHI DXIL is being stuck with a particular LLVM version. We'll see how that goes. So SPIR-V is great for that because it is well-defined. It's not tied to an LLVM version, and I think that's very important going forward. The state of the development, I would say it's ready for serious use. There are games shipping with it. I know Molten VK, but it depends on game shipping with Molten VK. I know at least Dota 2 and Metal as mentioned earlier. It's part of the Vulkan portability initiative, so whenever Vulkan on DX12 becomes a thing, it's going to go through SPIR-V cross, so that will be fun. It's also used by various open source projects, used by Roblox for their Metal backend. And I really want SPIR-V to become the one true shading language, and everyone should target it, and SPIR-V cross will just keep the older craft running, essentially. That's the goal. So I would like to see that there are various projects now that actually compile new languages into SPIR-V and use SPIR-V cross as a way to get the older stuff working. So, of course, I don't have infinite amount of time. I have a day job outside just hacking on this thing. So I prioritize bugs over features. I try to be as responsive as possible, usually a few days to get the bug fixed, but features can take forever or a very long time. So I kind of want to encourage more contributions for features, not necessarily bug fixes. I can probably deal with them. But if you want a particular feature, I'm probably going to hope that someone actually contributes it. And there are several regular contributors, so it shouldn't be too difficult. So some stats on the issue tracker, it's mostly enhancements now. Not too many, and many closed. I think that's healthy. I really don't want to see 5 new bugs on a Friday evening. That's very stressful. I don't like pull requests to linger, so 0 open pull requests and 302 closed. I'm happy with that. Of course, 220 of those are probably mine, but anyways. Because I go through Travis to make sure I don't break metal. So I have this habit of going through pull requests for everything. It's still going strong. It hasn't slowed down. There was this peak. I guess this was HLSL, a flurry of commits, but yeah, it's pretty steady so far over 2 years. There are some non-trivial missing features. So fortunately, no one has really asked for this, like with a strong reason for having them, like HLSL tessellation geometry, metal. Well, there's HLSL tessellation and geometry shaders. Those will be pretty terrible because HLSL is very different. Metal, fortunately, doesn't have geometry shaders, but it has tessellation, so who knows. But yeah, no one has seriously asked this feature yet, so please don't troll me and open an issue after this. Yeah, so that was it. Yeah, hope that was an interesting look into the world of cross-compilation. So I think there is a little time for questions. 5 minutes for questions.
That was great talk, thanks. You mentioned there's kind of a lot of connecting dragons with certain sort of this code. Is there a sort of concept of optional warnings to turn on and say, hey, be careful doing this because it's going to, make your legacy code look weird?
So the question is about buffer packing and if there are any warnings, like if there are dragons in your code that will probably not work on other targets. No, there aren't really any warnings, but there is validation. So it will strictly, at least for metal, GLSL and HLSL, I'm pretty sure it's for metal as well, where it will validate your buffer layout and see, can I express this? If it can't, it will throw an exception or assert or do whatever. But it will refuse to compile a shader that it knows will not work. Right. If there are no more questions, I'm sure you will troll me at the beer festival for this. So, thank you.